Okay, so let's talk about 2D. 2D is a little more interesting, but we want to follow this same philosophy because the 2D, as you'll see right away, is going to give us a little bit more complications, but we still want to use sort of this Lagrange polynomial coefficient idea. All right, so first we've got to do a cool drawing. Okay. Ready for a cool drawing? Yeah, everybody? Great. Me too. Let's see how I pull this off. Here's my x, here is my y, and here is my function, xy. And I have basically some surface, let's say. This is my solution, exact solution. What I'm trying to do with this exact solution is represent it by triangles, patches of triangles. Okay? So let's draw one in here. Okay? So now I have I, J, K. So instead of actually having the exact solution, I'm going to approximate this little patch here by a plane. Right? There's my plane. And let's do a projection down onto the xy axis. Are you feeling three-dimensional yet? Me too. Me too. It's all, you don't even need 3D glasses for me. I'm like for real. Except for you guys at home. Put them on now, because you guys. All right. So there we go. This is our points, and you know this point here is my xi, yi, and then you have xj, y sub j, and this point here is x of k, y sub k. Here's my projection triangle. And by the way, the area of this triangle is S. Let's call it S. You'll see it play a role later. So question is, how do I approximate that triangle? Well, you're going to do it the following way. You're going to take this thing and you say, my approximation is going to be A plus BX plus CY. And I want to determine A, B, and C. Because once I get A, B, and C, I pretty much know how to represent the solution there given the points. And I can interpolate all the values on a surface by constructing all these triangles. Okay? So, how do we do this? Well, first of all, here are my constraints. It has to go through the point, ith point. So I have A plus B xi plus C yi. That has to be satisfied. So if I put myself at xi, yi, it has to go through psi I. Also has to go through psi j, A plus xj plus cyj, and also has to go through k. Okay? So, 3 equations, 3 unknowns. Pretty easy to solve for. And we're going to solve for it the same way we did before. So we can construct these Lagrange polynomial coefficients. So we can have it for any generic functions versus just this specific ABC for one specific set of points. So we can rewrite this as the following. It's a vector system, as before, where psi will be my points of constraint. There they are. The matrix A will be my x and y values, and my unknown A will be A, B, C. As before, our objective then is to say, okay, I've got basically 3 equations, 3 unknowns, and if I want my unknown A, all I got to do is figure out how to invert that matrix, which you can do. Okay, it's a 3 by 3, but you can write it down. Let me write down what we get out of this. invert that matrix, and you're going to be able to now you're going to be able to find A, B, C. And let me just show you what this 5x is. Remember, it's A plus bx plus cy. And what we're going to find here is that this is ni xy phi I plus nj xy phi j plus nk xy phi k. What do these n's do? These n's at any given point are either 1 or 0. That's our whole purpose of setting it up. If you're at xy, yi, what do you think the value of this is going to be? Sorry, what? I said I, right? xi, yi, that's going to be 1. And these are going to be zeros. And if I'm at the jth point, xj, yj, 0, 1, 0. And if I'm at the kth point, 0, 0, 1. That's how you set this thing up. So it's a very generic representation, and all you care about is if I'm at any one of the points, that turns on, or that, and the other ones are 0 everywhere else. And what does this matrix look like? Well, it's a little bit more complicated. Let me just write out what the ni component is. The other ones look fairly similar. Okay, the ni of x, y is equal to 1 over 2s. Remember we had that length measure before in the 1D case, the distance between. Now we don't measure the distance between. We measure the area of that triangle projected down to the xy plane. That's the equivalent. Okay? And then you have xi, yk, minus xk, yj, j. That's a j. There you go. Yep. Plus yj minus yk x plus xk minus xj y. There. Okay, let's just verify this. If I'm at xi, yi, what is the value of this? So if I'm at xi, okay, so this is now I have an xi, yj, and then I'm at yi, and then I have a minus. Hold on. Let me make sure all my, I'm pretty sure I wrote it down right in the notes, but I could be wrong. Anyway, here's the point. I'd also have the S formula here because this is not going to go to 0 at that point. If I'm at the xj, let's talk about the other ones that go to 0. That's easier for now, okay? Because if I put in xi, y, I'm going to get a bunch of stuff here, and this is going to be that S. So it's not going to be so clear that what the S looks like, right, from seeing. But if I'm at xj, yj, then I have xj here, and I have xj, yj, minus xj, yj, right? And then xk, I feel like I'm talking pig Latin. Xk, nixnay, okay, xk, yj, I have that, and then I have canceling there, and then here I already canceled that guy, and I have xk, yj, minus xk, yj, zeros. And I can do the same thing if I put in xk, yk. Okay? So these are either 1 or 0. 1 at the point it's at, the ith point, 0 at the other 2 points. 1 at the jth point, 0 at the other 2 points. 1 at the kth point, 0 at the other 2 points. So you can see there's an efficiency here in representing all your solutions, let's say, because once you write this thing down, you're kind of done. You're like, right, the Lagrange polynomial coefficients didn't really care what points you used. If you solve for A and B, like our normal ways, like with a backslash or Gaussian elimination, it would work for those specific points. And then if I moved my points, then I'd have to resolve it, the 2 by 2. Whereas this says, it doesn't really matter what points you give me. I just shift around the coefficients. Okay? These are what we're going to work with. So let's come back to here then and talk about how far we've gone. Okay, so talked about discretizing the domain, or we didn't talk about discretizing the domain. Depending upon your perspective, we talked about it sort of. Okay? And I hand waved it and said, I'm not really going to talk about it because we're going to do triangles everywhere. But we did talk about interpolating functions and how you would do that, let's say, with those triangles. You're going to basically build all your representation of the solutions. For what we're going to do, we're going to do simplex method. You're going to draw line interpolations, or in 2D, plane interpolations, be three things. By the way, you can think about generalizing this, right? Why stop at 2D? You could go to 3. And you have finite volume methods, right? You start thinking about building little cubes of volume and representing the solution inside those cubes of volume. Okay? All right, so we have this, and then the question is, you're going to already see that, okay, once I have these points, these are going to be related to whatever my equations are. So how do I build these? Well, remember, we have some kind of differential PDE. It could be advection diffusion. It could be the heat equation. Whatever happens to be, whenever you pick your partial differential equation to work with, that is what's going to ultimately lead to the formulation of this AX equal to B problem. Okay? All right. So that's where we'll stop today. And I know Friday, we'll keep going. Super exciting.